laboratory centrifuge rotates at 4,000 rotations per minute. Test tubes have to be placed into a centrifuge very carefully because of the very large accelerations. Part A, what is the acceleration at the end of a test tube that is 10 centimeters from the axis of rotation? So the type of movement that we're looking at here is going to be that circular motion that we have been learning about in this chapter. You can see on the left I went ahead and included a little visual of what a laboratory centrifuge basically looks like, in which you just have a little test tube that is being rotated very quickly mechanically. So for this problem, part A, we're trying to solve for acceleration, and the values that we're given are the angular velocity and the radius, and we can go ahead and convert those two values we've been given into their standard units, so we can solve the problem a little bit easier. So that's what I did. For the rotations per minute, I went ahead and converted it into inverse seconds by multiplying it by 2 pi, as one rotation is 2 pi radians, and then dividing by 60 seconds to go from minutes to seconds. And it ends up being 418.9 inverse seconds for that angular velocity. And then I also converted the 10 centimeters to meters, getting 0.10 meters. So yeah, since this is circular motion, we're going to use one of the equations we've been given in this unit, one of the circular motion equations, to use these given values and solve for the acceleration of the test tube. So one of these equations is the angular acceleration equals the angular velocity squared times the radius. So we have all the numbers given in order to solve for the acceleration, so we can just plug them in and solve, and it ends up being the acceleration of the test tube in the laboratory centrifuge ends up being 17,500 meters per second squared. Okay, part B. For comparison, what is the magnitude of the acceleration a test tube would experience if dropped from a height of 1.0 meters and stopped in a 1.0 millisecond long encounter with a hard floor? So this is kind of worded confusingly. It almost makes it sound like you're wanting to solve for g, which is that free fall acceleration, but what the problem is asking for is the acceleration that occurs in that really, really fast 1.0 millisecond long period in which the vial has some velocity and then hits the floor and ends up being 0 meters per second, ends up having it completely stops the motion. So acceleration has to occur for that, the slowing down of that vial to occur, or that test tube to occur. So the way that I solved this problem was first just solving for the final velocity, as if this was a free fall situation, and then using that final velocity eventually as the initial velocity and that 1.0 millisecond long encounter with the hard floor. So I used the givens that we have for this problem and one of our kinematics equations from one of the earlier chapters in order to solve for that final velocity that the test tube is going to be right as it's making contact with the floor. I used the v final squared equals v initial squared plus 2a times displacement. And once I isolated the final velocity and solved for it, I got 4.427 meters per second. So that's just the part 1 of part B. And then part 2, I went ahead and converted that 1.0 millisecond into 1 times 10 to the negative third seconds to make our units work out. And our initial velocity is going to be 4.427 meters per second. That's what we solved for in part 1. And our final velocity is going to be 0 meters per second, obviously, because the test tube will be not moving. So I used another one of the kinematics equations, the v final equals v initial plus at, and then I isolated a. So it's now just going to be the change in the velocity over time. Then you can plug in the numbers, and you end up getting that the